Okay, so this is Henry Robbins' protein synthesis project. We're going to start off with DNA here. So this is the double helix of DNA, and just to break that down because we were doing DNA replication previously, we're going to be looking at the breakdown of DNA here, which is, guanine, your nitronic base, which is guanine, cytosine, adenine, thymine. They're held together by hydrogen bonds. You've got your phosphate group and your sugar backbone. So what protein synthesis does is it takes the information that is stored in DNA and it codes it into proteins that carry out what that DNA says. So that happens within the nucleus, and this first process called transcription. This little line delineates the nucleus, inside the nucleus, outside of the nucleus. So transcription happens when a DNA double helix is essentially split up. So it allows mRNA to get inside there, and mRNA matches up complementary bases with the DNA. So it reads the DNA, matches it up using RNA primase. Important, it does not have a thymine. Instead, it has uracil. And so uracil is essentially replacing thymine in this situation. And not all DNA codes, only some does in the nucleus itself. But so it takes the nucleus, or it takes the DNA, splits it apart, gets the mRNA in there, they set it up, and eventually after that is set, which takes a while because the mRNA has to revise itself, it leaves the nucleus, right, and comes down into the mitochondria, which is outside of the nucleic wall, and it matches up with an rRNA, which is a ribosome, and the ribosome is there to make the protein. It's like the factory for the protein. So it matches up here, and it matches up so that there are pairs of 3, right? Those are called codons. So codon is just 3 different bases. And so what happens is inside of the mitochondria, there are these little tRNAs, which each have an amino acid and 3 bases. And so what it does is it attracts tRNAs that match the bases, right? So here you've got an AUG. It matches a base, right? This here would be a UAC. So a UAC in this tRNA, which then, of course, carries an amino acid. And so that's actually the start amino acid to build that polypeptide chain. So what's happening here is you get another tRNA that comes in, it matches up, it matches up to these 3 bases, and there's always 3 slots in a RNA. So it matches up, it makes sure that there's an anticodon to the codon that is complementary, and then it starts building the chain, right? So this amino acid comes off, the tRNA moves down, amino acid comes off, right? It's built, it's starting the process. The ribosome moves up the mRNA, the tRNA moves down, right? And another tRNA is attracted by this codon because it has the complementary anticodon with a complementary amino acid, right? So you get here the 3 TNA slots. This one has already been used to build. The amino acid pops off, it bumps this up, there, right? So now this TNA is built. It moves down to the next set of codons. This comes out, back out into the mitochondria. This tRNA moves down, this TNR moves down, right? Then another tRNA is attracted in by this final codon here, this UCG, and the process continues so that eventually this one pops off, so that the polypeptide chain keeps being built, right? It moves down so that this comes off, this moves down, this is here, and of course the mRNA is much longer. I've shortened it for demonstrations purposes. So this chain just keeps getting built. So yeah, eventually, once these amino acids build up into a proper polypeptide chain, that protein, for example that protein of various amino acids is then used to carry out different things that the DNA, way back in the transcription phase, was coded for. And this entire process is called translation. So translation is just matching the anticodons with the codons to create those amino acid chains, which are proteins themselves in the ribosome, the RNA, using the mRNA. So this is the entire project. Yeah. Thank you.